We are continuing our discussion of Bernoulli's equation today, and homework 6, which, did you just turn that in today? So that had Euler's equation and Bernoulli's equation on it. This next assignment is just Bernoulli's equation and applications related to Bernoulli's. So that's due a week from today, and you'll be able to address the majority of the problems after today's lecture. We won't get to the rotational flow until Thursday. Looking a little bit further to the future, our next midterm exam is on Tuesday the 16th of November. Let me just make sure that I updated that date, because I want to make sure, yeah, Tuesday the 16th of November. So we've still got some time. The second exam will cover chapters 4, 5, and 6. So right now we're in chapter 4. Chapter 5 I've already kind of spoiled for you in lab last week when I told you that Q equals VA. I mean, that's the majority of chapter 5. And then chapter 6 is some wild stuff. We'll get to that soon. But so we're going to talk about Bernoulli's equation. Any questions related to the scheduling and announcement stuff before we move on? All right, well, let's do a bit of review related to acceleration. You may have the answers there in the notes, but if you do, don't peek. Unsteady flow is caused by what type of acceleration? Remember, unsteady is where conditions are changing with respect to time. So what kind of acceleration is that, where velocity is changing with respect to time?
Is that convective?
Nope.
Local.
Local. It's local. Right. Good. Local acceleration. Okay, now convective acceleration is associated with what flow type? So convective acceleration is the kind of acceleration that you'd see in a nozzle. So what type of flow is that? Now remember, laminar versus turbulent is related to the fluid's velocity, not so much the type of flow. Non-uniform is right, because when you have non-uniform flow, that is when the velocity is changing with respect to position. And so like the converging nozzle, where the velocity comes in slow and exits fast, that has experienced a convective acceleration, because it's not that its velocity changed with respect to time, it's that its velocity changed with respect to its position in the flow field. These are questions that I used to give in quizzes. You notice we haven't had any quizzes this semester. I may start again, but during COVID it became essentially impossible to have quizzes. So, quizzes are good spot checks. Like if you do bad on a quiz, it's better to have a disappointing score on a quiz, which is only worth maybe 1% of your final grade, than on an exam. Sometimes they can clarify the mind a bit. So what equation describes the relationship between pressure and local acceleration? So local acceleration is associated with unsteady flow. So what equation talks about how pressure changes due to local acceleration? Euler's. That's right. Good. And of course, Bernoulli's equation describes how pressure changes with respect to position. Right. All right. So here is a little animation that illustrates the Bernoulli effect. And what it shows is that the velocity of the fluid over the top of the wing is faster. Now, the reason why the velocity is faster is, think about some packet of air that reaches this front leading edge of the wing at a certain time. It's got a longer distance to travel to make it over the top of the wing than the bottom. Let me exaggerate the shape even more, the shape of a wing, just so it becomes really obvious. So here's a wing. That's not very good. I'm holding my breath. All right, now I'm behind the shield again. All right. So let's see. All right, so you can see that the distance, here's the stagnation point and here's the end. And so the total distance over the top of the wing is long on a relative basis, whereas on the bottom of the wing, the distance is short. So there's just less distance that a fluid particle has to travel in order to make it to the end, the trailing edge of that wing. And so what that causes is faster velocity is associated with lower pressure. Remember, that's the Bernoulli equation effect that we saw in lab last Tuesday, was that when the water was flowing through the throat of the tube, the piezometer was low. So the water level wasn't rising very high because the pressure was relatively less when the velocity is faster. So Bernoulli's equation says, if the elevation is the same, so let's ignore the z, P1 divided by gamma plus V1, Z1, plus V1 squared divided by 2g is equal to P2 divided by gamma plus V2 squared divided by 2g. I'm just going to write off to the side here for Z1 equals Z2. All right, so what it says is that if here at 1, you've got a certain pressure and a certain velocity, and then the velocity increases over the top of the wing. If the velocity goes up, the pressure has to go down because the sum of these two terms is constant. And so that's what's happening on the top of the wing. You hear about lift. Like, lift isn't some magical, thing that can't be understood. It's just the relative pressure difference between the top of the wing and the bottom of the wing. So the difference in pressure integrated over the surface of that wing. You can calculate the lift in newtons. Remember that force is pressure times area. So the pressure difference between the top of the wing and the bottom of the wing that's caused by the difference in flow velocity. The difference in flow velocity causes the pressure difference. And then if you multiply that by the area of the wing, then that's the lift force that can be generated by the wing. All right. Let's watch a little series of demonstrations. This guy's the best. Hold on, caricature of himself, but there's a phrase that he repeated several times, and that is that the increase in velocity gives rise to a diminution in pressure. And that's maybe a little bit overcomplicated way to say velocity goes up, pressure goes down. Right? So there were a series of demonstrations where, because of an obstruction, the flow of air was accelerated to pass through or between an obstruction, and so the air velocity increased, the pressure decreased, and so he was illustrating the effect of that pressure decrease, like when the two balls went together, the two croquet balls, or when the little ping pong ball was stuck in the funnel.
So does that mean tornadoes are so destructive because of Bernoulli's equation?
Bernoulli's equation, tornadoes. And that's an interesting question. I mean, heavy-duty storms are generally associated with low pressures, and it's low-pressure areas that wind is moving towards. But I guess I don't know enough about tornadoes to say that this is like a good illustration of the Bernoulli effect. There may be other stuff going on as well, but that's an interesting question. All right. So hopefully that's useful just to cement in your mind the main takeaway of the Bernoulli equation, which is that increases in velocity cause decreases in pressure. Now, one application of that is with a stagnation tube. And you can think of a stagnation tube as simply being similar to a straw. Like, what would happen if you inserted a straw into a stream of water that, or any fluid that's moving along? So here you can see, let's consider this as a plastic tube. So this doesn't have anything to do with the capillary effect. And so ignore what we've talked about previously in terms of small diameter glass tubes and how water level may rise due to that. even aside from the capillary effect, water can rise in a tube simply because there is an increase in pressure at the stagnation point. And so here at location 1, in a stream where the water is moving from the left to the right, water has a certain amount of pressure, of course, because it's down beneath the water surface. So it does have some pressure, and it also has velocity at 1. But then, if we follow the streamline, some of the streamlines above location 1 will go up and around the stagnation tube. Some of the streamlines below it will go below the stagnation tube. But then there is a streamline that terminates right at the stagnation point. And so that causes the increase in pressure that causes a rise of fluid inside of the tube. And we kind of already talked about this in Thursday's class with that differential manometer example, how there was a stagnation point in the nozzle where an air was flowing through. And so a similar thing is happening here. And so here's Bernoulli's equation written in terms of pressure rather than in terms of pressure head, where we've got the pressure gamma times Z1, and so collectively these two terms are the piezometric pressure, representing the amount of potential energy in the fluid. And then here is the velocity term. And so if we take velocity and square it and multiply it by the fluid density, then we'll have units of newtons per meter squared, just like the other two terms as well. So this says, Bernoulli's equation, written in terms of pressure, is that the sum of the energy here at 1 is the same as the sum of the energy at 2. And remember that the assumptions behind Bernoulli's equation is that we're applying it along a streamline for steady flow, where the fluid is incompressible and inviscid. So we've talked about how really there's no fluid that meets both the inviscid and the incompressible assumption. And so Bernoulli's equation is never going to be perfect, but sometimes it's good enough. And so what this Bernoulli's equation is saying is that we can predict how high the fluid will rise above the base water level. So D just represents how deep beneath the water surface that stagnation tube is inserted. But L is how high the liquid level rises above the surrounding liquid level on account of the extra energy that's being transferred from the velocity at 1 into additional pressure inside of the tube. So location 2 in this equation, we're going to say is inside the tube, where conditions are static. There's no fluid moving in the tube, but there's extra pressure because all of the energy that was as velocity had got exchanged. And so if we acknowledge that 1 and 2 are at the same elevation, just simplify Bernoulli's equation by canceling out the z terms. So that's where we're at here on the left. And then we can rearrange that if we know that V2 is 0. So there's no velocity at location 2 because that's inside the stagnation tube. So I'm saying V2 is 0. And let's just group the pressure terms together. And then solve for V1 by knowing what is the pressure at 1. So the pressure at 1, even though the fluid is moving, we can't say that the pressure is only affected by the hydrostatic equation, but pressure still does increase on account of the fluid depth, even in flowing fluids. And so hydrostatic equation applies, but then also other things apply as well on top of it. So what we're saying is here at 1, just because it's a certain depth under the water surface, we can determine the pressure by multiplying the depth by the unit weight. So that's the same thing as delta P is delta H times gamma. It's just here our delta H is the depth D, some distance. P2, so inside the tube, let's apply the hydrostatic equation. And so this stagnation tube is open to the atmosphere. And so the pressure is 0 at this interface. And then it increases as you go down through the fluid. And so the pressure at location 2, remember 2 we're saying is inside the tube. the pressure here is the depth multiplied by the unit weight. And so the depth under the water surface is L plus D, because the pressure is 0 at this interface, and then we're going down and the pressure is accumulating. And then when we go sideways, nothing happens to the pressure when you're moving sideways through a static fluid. So we substitute in our known pressure at 1, our known pressure at 2, and then cancel out like terms. This gives us that the velocity at 1 is the square root of 2g and then L, some distance above the water level. So if we know the velocity at 1, we could calculate how high the fluid will rise in the stagnation tube. Or you can use the stagnation tube as a crude way of approximating the fluid velocity in the stream. So you could use, in theory, a straw into a river, and you measure the deflection of the water, and then that would tell you the velocity because of the stagnation effect. So this kind of just tells us where we get this equation. V is the square root of 2gl, where L is some distance. And we're going to see this in the lab today. Today in the lab, we're going to use Bernoulli's equation to calculate the flow velocity out of an orifice. And the orifice equation is usually written in a similar way to what you see on the screen there. But the velocity is 2gh. So the square root of 2gh, where what we're saying h is the, we have a tank with an orifice in it and water's coming out. You can find the velocity at location 1 by knowing the depth, and then the velocity of the jet that goes out of the orifice is square root of 2gh. So this orifice equation actually comes from Bernoulli's, because what we say is, you know, here is location A, here's location 1, and so we say that P1 divided by gamma plus Z, I guess we're calling this A, the first location. Pressure at A plus ZA plus VA squared divided by 2G is equal to pressure at 1 divided by gamma plus Z1 plus V1 squared divided by 2G. And so here at the top of the tank, the pressure, where we're right at the interface of air and water, the pressure is 0. And the velocity at A is 0, because either there's water coming in to keep the tank height steady, and that will be the case in the lab today. We have water coming in so that it's always a constant head in that tank. But even if it was going down, it's going down relatively slowly, because we've got a large diameter tank, and so we can cancel out the velocity at A term. And the pressure here at 1, I think I gave you a hint via email that whenever water comes out of a tank or a pipe, it takes on the pressure of the atmosphere that surrounds it. And so as soon as the water goes out of the tank, that fluid jet has a pressure of 0, because there's air on all sides of it. Inside the tank, it still has pressure. So like over here, the water is pressurized when we're to the left of that orifice. But as soon as the water comes out of the orifice, it loses pressure. So there's no pressure at 1. So what we've basically got is ZA minus Z1 is V1 squared divided by 2G. So that's another way of us saying V1 is 2G times the change in height. So the change in height between ZA and Z1 is H to the 1/2 power. So square root of 2GH. So this orifice equation comes to us courtesy of the Bernoulli equation. All right. So let's use this equation to determine the minimum required stagnation tube length if you plan to measure a flow velocity of 2 meters per second at a depth of 0.5 meters. So let's just say, you know, the nub that's turned into the flow is just infinitesimally small. So we want to know, how long does the tube need to be if you're going to account for both the depth and the amount of rise that will occur if the fluid is going 2 meters per second. So let me pause for a second and allow you to calculate the minimum required length. Okay, so we know that at the very least it needs to be 0.5 meters long because we have to have it covering the depth, but then there's going to also be this rise L that needs to be planned for. And so if we rearrange this equation to solve for the length that the liquid level will rise above the base fluid depth, if it's going 2 meters per second, which is about 6 feet per second, it's moving quick, then the liquid level will be 0.204 meters above the surrounding fluid inside of that stagnation tube. So then the overall required tube length would be the depth that we're going to open up and intercept that stagnation tube, and then also the height that it will rise. So 0.704 meters plus however much length we want to have pointed into the flow. So like this distance, you'd need to also add on. Stagnation tubes are interesting, but just like piezometers, they're not particularly useful because they've got this open end at the top, and they rely on us measuring some length that could be really long depending on the velocity that's being intercepted. And so just like how piezometers are not as useful as manometers, stagnation tubes aren't as useful as pitot tubes. And so what a pitot tube is it's a differential way of applying the Bernoulli's equation. It's a way of measuring an increase in pressure simply due to the flow velocity. And let's look at this pitot tube that's it's intercepting air. And let's just assume that this is a top view, that we're looking down on this pitot tube from above. Although a pitot tube works even if it's not horizontally oriented. If this is a top view, just for simplicity's sake, let's say that it's horizontally oriented for now. So the air that intercepts the opening of the pitot tube experiences that stagnation effect. And so the pressure increases inside of the center of the pitot tube, and it's connected to a pressure gauge that's measuring how much higher is the pressure in the central part of the pitot tube. Then consider what's happening at location 2. The air is going around it, but the streamline isn't being stopped at the opening. So the pressure is less at location 2. It's just measuring the ambient atmospheric pressure. So that what the gauge is measuring is how much extra pressure is there in the center due to stagnation compared to the ambient surrounding pressure. So if we think about this in terms of the Bernoulli equation, here at location 1, the fluid doesn't have any velocity, but it has more pressure. And at location 2, it continues to have its velocity. If you rearrange the pitot tube equation, what you'll find is that, of course, velocity at 1 is 0, so that cancels out. But the piezometric pressure difference at 1 and 2 can tell you what's the velocity at location 2. So any change in pressure that occurs is because of the stagnation. And the stagnation is a representation of how large the velocity is. So these are used in airplanes. As, you know, an airspeed indicator is effectively a pitot tube. And this piezometric pressures allows us to say that this works even if it's not horizontally oriented. If it is horizontal, if you're flying through the air horizontally, then the elevation difference between 1 and 2 can be ignored because Z1 and Z2 are equal. Z1 and Z2, it's not going to be that much of a pressure change due to elevation. You know, if they're just a couple of centimeters apart, the pressure doesn't change in the atmosphere very much through just a few centimeters of gas. Like if you go on your tippy toes, your ears don't pop. You're not that much higher in the fluid. The pressure just doesn't change much with air in the same way that it does with water. So although, you know, we can find out the delta Z between 1 and 2 if this was going down, we can account for that pressure difference due to the elevation difference. It's generally pretty small. All right, so let's take this pitot tube and turn it on its side, and let's find out if we know that the gauge has a range of 0 to 7.5 kilopascals, so that's the maximum pressure difference that can be measured, then what would be the maximum airspeed in kilometers per hour that we could measure with this kind of a pitot tube setup? So we're going to be assuming that it flies through air that has a density of 1.2 kilograms per cubic meter. And so if you know that that's the air density, then you can also determine what is the air unit weight. And let me just look at my notes here. Since it's horizontally oriented, though, Z1 and Z2 are equal. So it's just the change in pressure here. And of course, at location 1, the velocity is 0 because it's a stagnation point. So it's the velocity at 2 that this is going to be measuring. It's going to tell you what's the wind speed going past the opening at location 2. So we want to know if the maximum pressure difference is 7.5 kPa, then how fast could you fly with this pitot tube? Feel free to talk and compare answers and collaborate as I pause this. All right, so the change in pressure is 7.5 kilopascals. That's 7,500 newtons per meter squared. And if we just start with Bernoulli's equation and we say that we know Z1 and Z2 are equal and the velocity at 1 is 0 because that's the stagnation point, then what we're solving for is the velocity here at 2, which is where the wind is going past that opening, but it's not being intercepted. So it's 402.5 kilometers per hour. Once we convert from meters per second into kilometers per hour, we have to multiply by 3,600 because that's how many seconds are in an hour, divide by 1,000 to go from meters to kilometers. So this particular pressure gauge we could use to go from 0 up to about 400 kilometers per hour. And then if we plan to fly the plane faster than that, then we'd need a gauge that can measure a larger pressure difference because there's going to be an even larger increase in pressure inside of that pitot tube when the plane is moving faster. Any questions about that one? All right. Let's look at the second example here with pitot tubes. This one's a little more complicated because we've connected the pitot tube to a differential manometer and it's being used to measure the velocity of a flowing liquid rather than a gas. So here, this pipe has kerosene flowing through it. So the kerosene is flowing downward through the pipe, and so it's not horizontally oriented anymore. And so rather than just using the pressure, we need to substitute in the difference in piezometric pressure. And we're using mercury as the fluid in the differential manometer. And we know the deflection here is 18 centimeters, so y is 18 centimeters, and so what is going to be the kerosene velocity? And what you need to do is write the manometer equation between 1 and 2 through the tube. And so remember, the manometer equation is just apply the hydrostatic equation in an environment where the fluid isn't flowing. So let me begin to put that on the board just so you can see what I mean. We're going to start at location 1 and work our way through the pitot tube and the differential manometer until we get to location 2. All right, so it's the pressure at 1, whatever that pressure may be, plus the gamma of kerosene, because as we're going down through the pitot tube, it's kerosene in the pitot tube. So everywhere is kerosene except for this shaded blue area. The shaded blue area is mercury. So gamma of kerosene, we're going down the distance Z1 minus Z2. So now it would be, that's what the pressure is inside the pitot tube where conditions are static here at location 2. It was whatever the pressure was at 1 plus the difference. So going down is why we gave it a plus. Gamma is the rate of change, and delta Z, Z1 minus Z2, is how much vertical we went down. Okay, so now plus, because we're still going downward, the gamma of kerosene, and the distance that we're going to go down from 2 to this interface is L. So we're going down, the pressure is increasing. Sideways, the pressure doesn't change. Down, the pressure is increasing again. So we're up to this point, the interface on the right side of the differential manometer. So it's going to be gamma of kerosene multiplied by the distance L. Now we're going to go up through the fluid. So that's going to be minus, and the fluid that we're going through is mercury. So gamma of Hg, which is the abbreviation for mercury, and the distance is y, minus, and now what is the distance from this interface, so the left side of the differential manometer, up to location 2? So that distance is L minus y. So it's the overall distance L reduced by whatever the distance y is. And so here in parentheses, I'm going to say L minus y times the gamma of kerosene is equal to P2. So this is just working down versus up, pressure increase versus decrease, finding the pressure at 1 in terms of the pressure at 2 and all of the changes in between. So now if we group it, it says here in red, rearrange in terms of PZ1 and PZ2. So remember that PZ1, that means P1 plus gamma Z1. And PZ2 will be P2 plus gamma Z2. Okay, so let's just rearrange this equation a little bit. We've got P1 plus gamma of kerosene times Z1 minus the gamma of kerosene times Z2. Okay, I've expanded out this equation by multiplying gamma by both of the terms that was inside the parentheses. Plus the gamma of kerosene times L minus the gamma of kerosene of mercury, Hg, times y minus the distance L, gamma of kerosene. So here I'm expanding out the gamma of kerosene times L and also times the y. So now plus gamma of kerosene times y is equal to P2. So do you see why it's a plus? Because it's a minus in front of the parentheses, and then y itself was also minus. So I just expanded out this equation, and I'm going to cancel out a couple of terms. I can cancel out this gamma of kerosene times L, and cancel out this gamma of kerosene times L, because I had plus gamma of kerosene of L minus gamma of kerosene times L. So those two terms cancel out. And then if I rearrange this P1 times gamma of kerosene times Z1, this is P sub Z1. And then let me just rewrite it. P1 plus gamma kerosene Z1. I'm going to move the P2 over to the left-hand side of the equation, so minus P2 minus gamma of kerosene Z2. So here is the P2 from the right side of the equation that's moved over to the left, and we still have the gamma of kerosene times Z2. And now I'm going to move these other terms to the right-hand side of the equation. So gamma of mercury times Y moved over to the right, and minus gamma of kerosene times Y moved over to the right. All right, so I just rearranged so that I can say this is P sub Z1, this is P sub Z2. So the P sub Z1 minus P sub Z2 is equal to Y times the gamma of mercury minus the gamma of kerosene. Seems like we've seen this before, that the change in piezometric pressure is what a differential manometer measures. It measures the change in piezometric pressure. And so if we put the change in piezometric pressure into the pitot tube equation, then we're going to be able to find out what is the flow velocity of the kerosene here. Because remember the pitot tube equation, this is basically differential manometer. And then the pitot tube, equation that we're going to use is that V2 is 2 divided by the density times P sub Z1 minus P sub Z2. And then all of that is to the 1/2 power. All right, so let me pause for a second, and I'd like you to calculate if we have a mercury deflection of 18 centimeters, then what does that tell us about the velocity in the pipe? So you know the specific gravity of kerosene and mercury, and from those specific gravities you can find the unit weights. We know Y, and so then that gives us the change in piezometric pressure. All right, so the answer to this one, let's see. So we go through rearranging the manometer equation. We got the pitot tube equation, so we've just derived this differential manometer equation again. We'd seen it before. The change in piezometric pressure is what's described by the deflection in a differential manometer. And so the differential manometer tells you the difference in the piezometric pressure. We substitute that difference in to the pitot tube equation, and we have to know the density of the kerosene, the unit weight of the kerosene, the unit weight of the mercury. And so make those substitutions, and that tells us that the velocity at 2 is 7.47 meters per second. Okay, so just to summarize, this homework 7, which you're now working on, is due a week from today. This afternoon we have lab. Let's see. Is it A through? Is it the first half at 2 o'clock today? So then the second half at 3 o'clock. And please watch that video. It'll help make our time more efficient in the lab today. So I'll see you then.